Yeah. Milestone 2 is very long. Yes, it is. And that's why you should have started earlier. If you haven't done so. But, uh, yes, so like there is a big learning curve in Milestone 2, especially that this is the first time you guys use the ECE297 library, the graphics library. But once you get used to how to draw graphics, I don't think you will find it that difficult to at least have the required features ready. Now, it's an open-ended assignment with the extra features, so it really depends on how. I personally do not recommend. Can you guys hear me, by the way? Yeah, okay. Was it? Yeah, I don't know why it switched. Uh, my mic, I think it's because connected to my phone. Let me just. Sounds good. Okay. Uh, but you still can hear me, right? Okay. So, cool. So yeah, basically, it really depends on how much you want to spend on the milestone. It's an open-ended assignment, but I personally do not recommend to waste a lot of time on it. Like to just get that have extra half mark or so, because you guys do have a lot of other courses and a lot of midterms. So 200 hours, yeah, more or less. Like give or take 2 hours, probably. That's good. Uh, Okay, so just to recap what we done last week, we basically drew the intersections using the latitude and longitude. So if you remember, we had a callback function, which is called automatically every time the refresh drawing function in EasyGL is called. Okay, and this callback function is of type void, and it accepts as a parameter a pointer to an object of type renderer. This renderer is like the brush you use to draw stuff. So you can draw lines, arcs, uh, rectangles, etc. So in this function, we basically want to go over all the intersections and just draw them. Pro tip: don't actually draw the intersection, just draw the street. Yes, that's actually more reasonable to draw the three segments. But this is just an example to show you how to use EasyGL anyways. Okay, in this case, we are looping over all the intersections, and we set the x and y coordinates to be the longitude and latitude of the intersections, and we define some width through trial and error to be 0.001, but just because it looks okay on the screen. And then we draw each intersection by calling fill rectangle, which is a function under the renderer object. And this function basically accepts two parameters: the bottom left corner, or the coordinates of the bottom left corner of the rectangle that you want to draw, and the top right corner of the rectangle. So in this case, it's xy and x plus width, y plus height. Is it possible to rotate the entire frame in EZGL? That's a good question. I'm not sure. Uh, can you like? I'm not sure because, well, the initial word is a rectangle object. So if you rotate that rectangle, I'm not sure what happens, but you can try it. I haven't tried it before. Okay, so once you basically this is the draw main canvas, or the main callback function that we want to draw, and then other than that, we need to, in our main draw map function, we need to define the initial words. In this case, we set them to the minimum and maximum latitude and longitude. Remember that we want to match the coordinates of the intersections that we are drawing to the coordinates of the word. So that's why we first find the minimum and maximum latitude in our city, and this is our world's coordinates basically. And then we define our canvas through its ID, and we pass the name of the canvas function, which is, in this case, we are calling draw main canvas xy fixed word. This is the main callback function that we use to draw the intersections. And we also pass the initial world coordinates to the canvas to define what is the drawing area. And remember, basically, finally, we have this application.run function. And this is the function that keeps running until you exit the program. And if you look here, it accepts 4 different pointers. These are pointers to other callback functions that you can use to have certain functionalities triggered when certain things happen. For example, you can have a callback function when the mouse is clicked or the mouse is moved or the one of the keyboard keys is clicked. So we'll see an example later on in this tutorial how to do this. For now, it's just we have just a dumb application. It doesn't do anything else other than drawing the intersections. Uh, okay. So this is how it looked, if you remember. And if you can, someone tell me if this looks right or no, or like, is there any problem with this? Yeah. So it's not that I forgot the scale. It just looks a little bit squished from top and bottom. It's not using the whole drawing area for some reason. And we're not going to do the demo. We basically saw it last week. We'll do the demo for the next part anyways. So the problem with that is we are using the latitude and longitude as our coordinate system. I don't know what Toronto looks like, so I'll never know. Well, it looks like something like this. But if you look at Google Maps, for example, you will find that the top and bottom edges are a little bit stretched outwards. Uh, and the reason why it's squished here is, again, we are using the latitude and longitude coordinates as our latitude and longitude degrees as our coordinate system. And if you look at the latitude, for example, of Toronto, you will notice that the difference between the maximum and minimum coordinate or minimum latitudes is around half a degree. So basically, it's using the latitude and longitude coordinates is not representing the Cartesian distances between different points in the map accurately. So first, we need to transform these latitude and longitude coordinates to actual Cartesian coordinates, so you can use Pythagoras theorem to measure distances, for example. And we also need to define our coordinate system to be based on Cartesian scale, not on latitude and longitude, so that we don't have this. Because as you go further from the equator, the latitude differences start to become smaller and smaller, and the distances start like the distance become unreasonable, or they do not make sense. So if you remember from milestone 1, we basically gave you like a formula to transform from latitude and longitude coordinates to x and y. We will use this function. We call it here x from lon and y from lat. In order to do this or pre-populate our data structures beforehand with these coordinates instead of the latitude and longitude. It might also be helpful, as we'll see later, to have the inverse functions as well to get the latitude and longitude from the x and y Cartesian coordinates. Okay, so how do we modify our drawing canvas or our main callback function? Basically, instead of setting the x and y to the longitude and latitude immediately, we first transform them to x from lon and y from lat. To actually speed up your code, these should be done somewhere in your like load map or somewhere where you can pre-populate data structures, and not every time you are drawn. But for just for the for this time, we'll just assume that we want to do it inside drawing canvas. So once you do this, your distances now start to make sense. Now everything is in meters actually. So you can like if you see that the difference between two different points is 100, that you know that it's actually 100 meters physically. And our width and height now make more sense. So in this case, we are defining the width of the intersection to be 100 meters. Now 100 meters for an actual intersection might be a little bit too big, but it just draws noise on the screen. You can obviously decrease it or increase it however you want. So What else is missing? Missing now that we've changed the draw main canvas. Is there anything else that we should do? We also need to, yeah, exactly, change the initial word as well, because we are defining here the initial word coordinates to be minimum lat and longitude. We first need to determine the minimum x and y from these, uh, and then set the initial word to the actual Cartesian coordinates. So that again, we need to match what the coordinates that we draw the intersection with to the coordinates that we use for our uh, word drawing area. So yeah, again, we basically call x from lon and y from lat on these four different variables. Okay, so now it looks like this. So now you were basically asking what it should look like. So if you compare it to the previous one, this looks more reasonable now. This looks actually more representative of the Toronto map. Let's go see it in the demo. So I have it here open. Basically, I'm going to call draw map fixed coordinates. And just to remind you what this looks like, this is the one. No. Oh no, actually we need the, is the tutorial for the whole 2 hours? No, it will take 1 hour, probably less, and we'll repeat it again in the second hour. Uh, but if there are no students like that want to attend the second hour, we can also make it a Q&A session if time permits. No problem. So yeah, this is our main draw map function. Let me just remove this. We're basically first calculating the minimum latitude and longitude of all the intersections in the map. And we are also pre-populating the intersection data structure that we defined, if you remember last week, which stores the position of each intersection and the name of each intersection. Then we calculate the average latitude that we will use to basically transform to the x Cartesian coordinates. And if you notice here, we set the initial word to x from lon on the minimum and maximum latitude and longitude. We define our canvas, and finally, we run the application.run with no other callback functions. So it's just a dummy application that just draws the intersection. It can zoom in, zoom out, obviously. And just to show you here, these are the functions to transform the coordinate system. So for example, to get the longitude from the, to get the x coordinate from the longitude, we multiply the longitude by the degrees to radians ratio times the Earth radius in meters, which are all both defined in m1.h, if you remember from last milestone. And then we take the cosine of the average latitude times the degrees to radian again. And so if you notice here, this formula contains four multiplications and the cosine. These operations are actually expensive in terms of runtime. And if you are doing them over and over again, they might make your map a little bit laggy. So I recommend pre-populating all the x and y coordinates for all the intersections in advance, maybe in load map, like once you load your map, before actually starting to actually drawing the graphics. And in our drawing canvas, we're just looping again over all the intersections, and our width is in 100 meters. Okay, let's compile this. Unused variable height. Where is this? So I got a warning, maybe because I changed something in the last tutorial. Whoops, yeah, this one should be. That's why it's important to look at the warnings. Although your program might work, but it's better to resolve all the warnings as well. So let's run the mapper. Okay. Yeah, now we can see that the drawing takes the whole drawing area, and obviously we can zoom in, zoom out. If we zoom on to the intersections, they are all squares of. Now this is you can see. You might not notice it, but this is basically 100 meters physically from this point to this point. Any questions so far? If not, then we can continue the slides. Okay. So now that we've drawn the intersections, we want to do more meaningful stuff. What if we want to react to certain actions that happen during the map? So, for example, we want to react to a mouse click. Uh, and let's say that we would just want to print the intersection ID or the intersection name of the closest intersection to where we click the mouse. So to do this, we need to define a callback function that does this for us. So in our application.run in DrawMap, the second the second parameter should be a pointer to a function that reacts to the mouse click. Now you can name this function whatever you want, but it should have this specific prototype. It should be of type void, and it should have these 4 different parameters. The first one is a pointer to the ECGL application itself. And this is usually passed automatically once you click on the mouse because you are passing this callback function to application.run. So the .run function will pass a pointer to the actual object application object to act on mouse click. There is another parameter of type GDK event button, and it's also a pointer. So ECGL is built on top of a graphics library called GTK, and GTK has the classes or data structures for different objects in the graphics. One of them is to define certain buttons, for example, or to define certain events. And for this case, it's called GDK event button. So this is also passed automatically by the application.run to the callback function. And you can use it to specify, to like check which button on the mouse was clicked. For example, you can, if you want certain functionalities to appear when you click on the when you click the right button of the mouse, or when you click on the left button on the mouse, you can basically query these things from the event button. And in NetBeans, when you type event dot something or event arrow something, it will list all of the member variables for this class, so you can use them. For example, the button ID that specifies which button was clicked is called, I think the variable was called button, and for the left click, it has an ID 1. For the right click, it has an ID 2 or 3, something like that. So you need to do trial and error to actually know which is which. But basically, using this, you can say you can add an if statement in this function to check, okay, if the left button or of the mouse was clicked, then I want to do this thing. For now, we just want to print the closest intersection to where the mouse was clicked. Whether you clicked using the left or right, doesn't matter. So, and the last 2 parameters basically are the x and y coordinates in double of where the mouse was clicked. So given these, how can we check for the closest intersection? Can someone tell me what we should do in this portion of the code? Use our function in M1. Yes, exactly. Which is the find closest intersection. But remember, in M1, the find closest intersection took the position as latitude and longitude. So that's why first you need to transform these x and y coordinates, because our coordinate system right now is in Cartesian, from x and y to latitude and longitude by calling the inverse functions to our transformation, which is the latitude from y and longitude from x. I think these should be reversed probably, but anyways. Or no, actually the latitude comes first. Yeah. And once we get the idea of the closest intersection, we can basically query our pre-populated data structure, which is the intersections, to get the name. And that's it. We just print the name. But what if we want to do more stateful graphics or more meaningful stuff? Let's say that we want to actually highlight on the graphics the closest intersection to where the mouse was clicked. So how can we do this? Any ideas? You might not know this, obviously, but just if you have any idea, you can type it in the chat. Okay, so we can basically add a new member to our intersection data structure called highlight. This is basically a boolean that either takes false or the value false or true. If it is false, then we want to use the default color to draw the intersection, which is gray. If it's true, then we wanted to take any other color, let's say red. In our callback function to act on mouse click, once we get the intersection ID of the closest intersection, we can set the highlight value of that intersection here to true. What remains is to actually check for this highlight and draw in different colors. So where do we do this? Basically, we do it in our draw main canvas function. Remember, the drawing, most of the drawing is done in the main canvas callback function. So before drawing filling the rectangle, we need to define the color. So we check if intersection of I is highlighted, then we set the color to red. Otherwise, we set it to the default one, which we used before, gray 55. Any questions on this? Okay. There is something else missing in here, in that remember that the draw main canvas or the callback function will only be called when you call refresh drawing. This refresh drawing will automatically be called, like for example, if you zoom in, zoom out, zoom fit, pan right, pan left, etc. But if you don't do any of these, the refresh drawing will not be called. So you will not see the highlighting immediately done on the screen without this. For this reason, we need to also, in our act on mouse click, once we update the highlight to true, we need to refresh the drawing to tell ECGL that okay, you should redraw right now. This refresh drawing, basically what it does is it clears the whole screen and then draws calls draw main canvas again to draw the whole thing. This way you will immediately see the highlighting takes effect. Okay, so let's go see this in the demo. So we want to run another demo in here. And let's go look at what this function does. So this is the main draw map function. Again, we're just looping over all the intersections to query them. And we are defining our initial word. The only difference in this function from the one before is that now we are passing another parameter, which to application.run, which is a function pointer called act on mouse click. So let's go look at what this function does. Okay, so this is the function, and similar to what we saw in the slides, we are getting the position, latitude and longitude position of where the mouse was clicked, and then we are calling our M1 function, find closest intersection. Then we are highlighting this one to true. But let's say that for now, we don't want to refresh the drawing. Let's see what happens. Okay. So every other thing is the same. Oh, and this is our draw main canvas function. We are checking if the highlight is set. If yes, then we set the color to red. If not, then we set the color to gray. Let's go compile this. And here we got a warning because now in our act on mouse click, it says that we have a parameter called app, but we haven't used it. We haven't used it because I commented out the refresh drawing in this case. In any case, if there are parameters passed to certain functions in ECE297 and you don't want to use them. For example, in this case, we are not using event, and you want to remove the warnings before submission, you can just comment out the parameter name by only keeping its type in the prototype of the function. Okay, so now that we compile, let's go run the mapper. Okay, maximize this. And let's zoom in a little bit. So now I will click the left mouse click on here, and you can see that nothing is happened. The reason behind this, because we didn't refresh the drawing. But if you press, for example, on zoom in, you will notice now it's highlighted. You can also press on zoom fit. I just clicked on this region as well. And oops, actually zoom fit was a bad decision. But anyways, you can see that another intersection was highlighted. So let's go fix first the refresh drawing thing and see if it happens immediately. Okay, so let's zoom in. And now I'm going to press somewhere. So yeah, you can notice that it immediately takes effect. You don't have to zoom in or zoom out because we automatically call refresh drawing after each press. Okay. There is another subtle bug that you might not have noticed. Let's say that I will press the mouse button in here. So the closest intuitively is this one, but it highlighted this one. Can anyone know what is the reason behind this? Why is this happening? Okay, yeah, you know, but what is the reason then? The boxes are placed at the wrong location. Yes, that is actually true. So remember when we drew the intersections, we said that the fair rectangle takes two parameters: the lower left corner of the intersection and the top right corner. And basically, our intersection positions that we are given from Street Database API, they actually point to the middle of the intersection. But in our code, when we are drawing, we are saying that the intersection position is actually the lower left corner. So instead of drawing, uh, so basically we are drawing from here this way, okay? Instead of drawing from here to here. So to fix this, we need to update how we draw our coordinates. So let's go and fix that, how we draw our rectangles. So in here, instead of from x and y to x plus width, y plus height, we should do x minus width over 2 and y minus height over 2 to x plus width over 2 and y plus height over 2. Does that make sense? Okay. Let's go and draw another example like this. So let me zoom into where this might happen. Okay. This might be a good place. Yeah. So this is the closest one. This is the closest one. And let's see somewhere else. Yeah. See? So it didn't highlight this. It highlighted the one that is actually closest to it. So any questions so far? If not, then we can proceed. Okay, so now we have drawn the intersections. We have seen how to react to a certain action like the mouse click or how to define our callback functions. Let's say that we don't like the layout of the window and we want to change it. So how do we do this? So if you look under your resources folder under left street map, you will notice that there is a file called main.ui. This main.ui is a human readable XML file that is not CPP file, and you can actually open it in any editor and edit it. This file defines the layout, how the window looks like once you open it, or once you open the EZGL application. And if you remember in our draw map function, the first thing when we define the settings is that we need to specify what is our main layout by passing this path. So under resources folder, you usually store everything that is not CPP code. For example, if you in your milestone 2, if you want to show like different images for different POIs like hospitals, etc., you store these images under this folder. So how do we modify the main.ui? Again, you can either open it in an editor, but you can also do it graphically, which is easier. To do it graphically, you basically type a software called Glade. We use a software called Glade. You type Glade and the name of the file or the path to the file. So let's go see how to do this and what kind of stuff you can do. You can basically rename components if you don't like the naming. You can move components or windows around. You can add a new components, remove components, etc. So you don't have to actually in this milestone to change it, but if you want, you can do so, obviously. So let's go actually look at the, oops. It's stuck. Okay. So what is it? So I'm going to call Glade on libstreet. Oh, libstreetmap resources main.ui. So once you open it, it will ask you to do a survey, never mind. And this is how it shows you how the window or our main layout looks like. Remember that ECE297 is built on top of the GTK library, and the GTK library deals with graphics through certain data structures. The main window is of type GTK window, and you can see it here on the left part of the screen. If you click on it, you will notice that this GTK window has different parameters. And for example, the ID that we specified in our code was main window. So if you change this ID in here, you need to change it also in the code so that ECE297 knows where is your actual layout. If you expand main window here by clicking on this arrow, you will notice that it has another data structure under it. And this data structure is of type GTK grid, and it defines the overall grid, or how is the screen or the window divided. So if you click on this object, which is called outer grid, you can notice that it says here it has 2 rows and 2 columns. That means it has 4 different cells in total. And in each cell, you can do different stuff. You can add new buttons, you can add new windows, etc. You can also add grids within grids. Actually, if you press on the arrow sign here, you can notice also there is a grid inside this outer grid. And there is also an object called main canvas. This is the main drawing area we have, and it is of type GTK drawing area. And this is one component of the overall grid. So it occupies only one cell. The status bar here occupies 2 cells. Sorry, the status bar here, occupies 2 cells. And there is also an inner grid. An inner grid is, we drew it this way to basically put all the buttons inside it. So if you look at the inner grid properties, it has 7 rows and 3 columns, and you can actually count them: 1, 2, 3 columns, and 1, 2, 3, 4, 5, 6, 7 rows. Obviously, you can decrease these. You can remove all of these buttons if you don't like them, and like you can replace them with something else. For now, we'll just keep them. Okay. So this is basically a brief description of how the window is defined in ECE297 and GTK library. Now let's go run our application. Before editing, I wanted to show you something again. If you notice that the title of the window is ECE297 application example. Obviously, this is not a good name for a graphics for our graphics window. and we need to rename it to something more meaningful, like an ECE297 map or something like that. And we do this through Glade. So we open it again in Glade, and you go to the press on the main window, and under the properties of the main window, you can see here that the title is grayed out, and it's EaserGL application example. To edit it, you need to uncheck this box, and now you can edit it basically. Let's say call it ECE297 map. Okay. And then you save it by either pressing on the save button here on the top right or Control X, Control S. Sorry. So once you save it, you can close this, and you obviously don't have to recompile anything because we didn't change any CPP code. And let's run. So once you run it, you can see that the title of the window changed, EC297 map. Can it also be done from the program itself? Yes, but I don't think EaserGL gives you this ability or doesn't have the interface for it. I think you need to dig deep into GTK library, which is a lower level than EaserGL. Unless I'm mistaken. But last I checked, there wasn't an option for this in EaserGL itself. Does that make sense? Cool. So this is basically how we edit the main window if you don't like it, or if you want to make it more user-friendly, for example. And these are all the materials we have today. So if you have any questions, I'm happy to answer. If not, then I'll see you next week. Could you do a demo to creating a test button? Yes, sure. Okay. So basically, let's go first. And could you do a demo for the entire M2 and post the source code? Yes, I can do that, but after the course ends. I don't seem to be able to create it after following the handout in the example. Okay, yeah, we can do that. Let me actually stop the recording because so that we don't annoy other people.